This is a short extra talk to finish off the material of section 7.2 on the Euler characteristic, which I didn't have time to do in the live lectures. So the Euler characteristic, or the Euler number, is some integer which you can associate to a surface. And the easiest way to think about this is you take a triangulation of the surface. So we've broken the surface into a number of triangles, and when I say triangles, I just mean something homeomorphic to a triangle that might have curved sides depending how you represent the surface. But you can certainly count the number of vertices overall, the number of edges, and the number of triangles. And it turns out that whatever triangulation you choose, the quantity, this alternating sum consisting of V minus E plus F, does not depend upon the choice of triangulation. And this number, normally written chi, Greek chi, is called the Euler characteristic or the Euler number of the surface. Now, as I'll explain, you don't have to use triangles. So let me remark first of all, if you remember from discrete mathematics, if you did it, in the discussion of planar graphs, we saw that this combination V minus E plus F, where you interpret F as the number of regions including the outside of the planar graph, this number is always equal to 2. And in fact, what's going on there is that a graph in the plane is really the same thing as a graph on the two-sphere, because there'll always be, we can always add a point and sort of get the two-sphere. You can think of the plane as homeomorphic to the two-sphere minus a point. And the Euler characteristic of the two-sphere is 2, so that's why we always get this answer 2 for a planar graph. And we sort of proved by induction that this number is always equal to 2 and doesn't change when you add edges and so on. Now, in the case of surfaces, I mentioned it for triangles, but you can divide the surface up into any way you like. You can divide it up into polygons. The key thing is that when you talk about a face, that has to be a region which is homeomorphic to a triangle, or what I really mean is homeomorphic to a disk, any polygon. So provided that's the case, this formula will be valid. So for example, how do we compute the Euler characteristic of the sphere? So you can, for the sphere, you see all you have to do is you can choose any point of the sphere, say the North Pole, if you think that way. If you remove the North Pole, then what's left is homeomorphic. The open set that is left is homeomorphic to a disk. So in particular, you can count it as a face. So in other words, that's a valid subdivision of the sphere. It consists of no edges, one vertex, and one face. So the Euler characteristic is equal to 1 minus 0 plus 1, which is equal to 2. But of course, you can divide the sphere up into other ways. If you like, you could take here's a sphere, you could take the equator, and we could think of you see, we could have the northern hemisphere, which is homeomorphic to a disk, if you think of it as an open hemisphere, the southern hemisphere. So that would give you two faces. But there's something else I forgot to say. Your edges have to be homeomorphic to an interval. So we can't take a circle as an edge. So we have to break that up with at least one vertex. So having done that, we've got one edge. Or if you like, to be safe, we can take two vertices to be absolutely safe. Then this looks like just half the equator is just like an interval. So we have two edges in this case. So E is equal to 2. And the number of vertices is also equal to 2. So again, it's correct. We're going to have 2 minus 2 plus 2. And we always get the Euler characteristic of the sphere is equal to 2. And by playing with lots of examples, you begin to understand why this Euler characteristic does not depend upon your choice of subdivision, whether that be with triangles or other polygons. don't forget also that when you have a triangulation with lots of triangles, say, then you could actually split all the triangles up and think of them as individual words, which are then assembled together in the sense of our combinatorial surface. So a combinatorial surface could be one or more words. Normally we just have one word because we're thinking of a single polygon. But you could take a triangulation or division of the surface into any number of polygons and keep them separate, and just keep a number of words, then you'll have a lot of words, and that's still a combinatorial surface. You can still do the quotient by identifying the edges in pairs. They don't have to be on the same polygon. So in particular, it means that when we have two sort of combinatorial surfaces and we take their quotient, if they're equivalent by the operations which I talked about in the live lectures and are given earlier in these notes in 7.2, if they're equivalent, then it means that the surfaces you get by quotienting, by doing those identifications, are homeomorphic. So in particular, we want that this number, the Euler characteristic, this should be, if two combinatorial surfaces are equivalent with this tilde, with these operations, but by a succession of operations I talked about, the corresponding Euler characteristics must be equal, because these are two different triangles. They would correspond to two different subdivisions of the same topological surface. And you can check that they're equal, that all these operations I described do not change the Euler characteristic. Some of them don't change individually, V, E, and F, but others may change V and E by 1 unit, and they cancel out. So that's on exercise sheet 7. Okay, I'm just showing what's hidden under the insert. Okay, so that's the point. So I'm not going to give a rigorous proof of this proposition, but if you use examples, you can sort of understand why it has to be true. And a sort of special case of it we saw in discrete mass. Okay, so going on. Now let's go back to the situation in which a surface is modelled on a single polygon with an even number of vertices. So it's always talking about surfaces without boundary and at this point connected. Then the claim is that, how would we compute the Euler characteristic? We can use any subdivision we want. So what we can actually do is, because the interior of the polygon is homeomorphic to a disk or a triangle, we can use that as our face. So we can actually take F to be equal to 1 in the definition of the Euler characteristic. That's allowed, as I explained for the sphere. How many edges do we have? Well, if the polygon has 2 n sides, we know that when we do the quotient, the edges are identified in pairs, so we'll end up with n edges. So the number of edges when you have a polygonal model is obviously equal to n, because we're identifying the edges in pairs. If you start with a hexagon, that has 6 edges, but you're identifying the pairs. So on the surface, when you've done the equivalence relation, you only have 3 edges. Now the number of vertices, you see, you can think of this as what happens. You've got vertices around the polygon, so if it's a hexagon, you've got 6 vertices. But when you do the equivalence relation, some of these vertices will be the same. So for each vertex, there'll be at least one other vertex, which is equivalent to that. So the number of vertices will reduce when you go down to the surface, but it's not completely obvious how many vertices you get on the surface. So that has to be calculated each time when you have the word which describes the equivalence relation. Okay, so I'm going to explain this with an example. So you've seen examples already. We've seen, for example, these 4 square examples. In the case of the torus, I explained that all 4 vertices on the square are actually the same point on the torus, because remember, for the torus, we had this square model, but essentially it corresponds on the torus. The edges we had sort of correspond on the torus to these two circles, because there are only two edges after the quotienting, and you just get these just intersect in one vertex, which is the unique vertex on the surface. So for the torus, when we have the square model, we actually have one vertex. We have two edges because we've got a square, and we've got one face. So the Euler characteristic of a torus is 0, and that's correct. Okay, but we have to compute the number of vertices in each particular case. Okay, so let me do that now. Well, let me explain how this relates to perhaps normal form. So one nice thing about the normal form of a surface, of a combinatorial surface, remember the normal form is of one of two types. Either we have these combinations of AB, A inverse, B inverse, or we have combinations of double letters, AA, BB, and so on. And whatever the normal form is, you can check that you only have one vertex on the surface. That is, although you may have lots of vertices on the polygon describing the normal form for the surface, all these vertices around the polygon are actually equivalent to each other. So I'm going to give you an example of that now, but let's just accept that for a moment. If there's only one vertex, let's go back to our formula at the top. If there's only one vertex, then we just have to worry about the number of edges. So if there are, for example, in the case of the non-orientable normal form, the number of letters is 2h, not the number of distinct letters, but the number of letters altogether is 2h, but they're identified in pairs, so the number of edges in that case would be h. So we'd actually, the Euler characteristic would be 2 minus h. On the other hand, when we have the normal form with these groups of AB, A inverse, B inverse, we have each group is 4 letters. So altogether we have 4G letters, but they're identified in pairs. So in that case, N would be 2G. So the Euler characteristic would be 2 minus 2G, a very famous sort of quantum relationship. The Euler characteristic is 2 minus 2G. Always remember that for oriented surfaces. But I haven't justified this key observation, and I'll show you with an example why it's true. So here's an example of a normal form for an oriented surface. It consists of two of these combinations, AB, A inverse, B inverse, another typo here, CD, it should be CD, C inverse, D inverse. That's what I meant to write there. And these are just next to each other. I'll put the brackets just to emphasize, it's just punctuation to emphasize that. So this is a group, this is meant to be a string of 8 letters, okay, identified in pairs. So I've copied the string down here, but remember it's a sort of, it's really going around, we're really talking here about an octagon actually. So, you know, here we have 8 letters, so we could arrange those, we'd really have to arrange this around an octagon. And then the surface includes the interior of the octagon together with the 8 edges, which are identified in pairs. So really this is a cyclic business, because if this edge is A here at the start, then we go all the way round and we would finish here with so A would have the arrow in that direction, and we'd finish with a D inverse, so that would be D, with the arrow going backwards, going anti-clockwise. But here I've thought of it as a sort of linear string, and I just want to quickly show you why there's only one vertex. And that's using the equivalence relation on the edges. Of course, an edge has 2 endpoints, so when 2 edges are identified, the endpoints are identified in the correct sense. Okay, so let's just start at the beginning of A, which corresponds to this vertex here on the polygon. But there's another A, there's an A inverse somewhere. And the beginning of A is the end of A inverse. So I'll just connect it like that. Okay, and then this vertex here will be between A inverse and B inverse. So this is the beginning of B inverse, which is the same as the end of B. And the end of B is the same as the beginning of A inverse, which is the end of A. So these vertices are the same. Okay, and then the beginning of B is the same as the end of B inverse. So these vertices are the same. Between each two letters, there's a vertex on the polygon. I'm trying to find out which of those are equivalent on the surface. Now we're at the beginning of C, which is the end of C inverse. Now we're at the beginning of D inverse, which is the same as the end of D. Now we're at the beginning of C inverse, which is the same as the end of C. Now we're at the beginning of D, which is the same as the end of D inverse. And now I've gone through every vertex, and you see they're all equivalent because they've all been identified via the equivalence relation. This is a bit reminiscent of the DT code for knots, but sometimes you have to make crossings. So it's just you can use any scheme you like to try to find out when the points between letters are made equivalent. Okay. In fact, it's always so. If you do this with other examples which are not in normal form, you may have two equivalence classes. You can't separate. You don't necessarily have all the vertices equivalent. In that case, V would equal 2, or you might have 3 or 4 equivalence classes. So that will give you the number to plug into the Euler characteristic. So you can always work out the Euler characteristic of your surface. The other thing I really want to say, there's a typos here. It always turns out always that the sort of first and end vertices, even if you break the necklace, will always be equivalent. Well, that's a separate matter. Let me just emphasize, going back to this observation, that if the surface is oriented, its Euler characteristic is even. So if you find a surface and finding out the Euler characteristic helps you classify the surface. It's often a quick shortcut than trying to reduce the very complicated word into normal form, which you've seen can be very complicated. Often it's much quicker to use this formula, find out whether the surface is oriented, and you know that immediately, because oriented means you've got some letter repeated, like you've got XX or AA. To be non-orientable, you've got a letter repeated. If you want it to be orientable, there must be no repeated letter. So every letter has to be associated with its inverse in the word. But if you find a surface and you find the Euler characteristic is even, then it has to be, it's easier. If you find the Euler characteristic is odd, it can't be orientable. So you know what it is. Okay, if you find the Euler characteristic is even, there are two possibilities. Either the surface is orientable or it's not orientable, unless the Euler characteristic is 2, in which case it has to be the sphere. Because non-orientable surfaces start with a projective plane that has Euler characteristic equal to 1, and each time you add a projective plane, you reduce the Euler characteristic by 1. Okay, well, there'll be exercises on this, so I'll stop there.